my background in geoscience is a little bit varied. At the moment, I am working for the US Geological Survey, developing machine learning tools to identify locations that are favorable to geothermal or conventional hydrothermal resources. But my background is quite a bit different than this current postdoctoral position that I have with them at the moment. In my PhD research, I was a candidate at the University of Canterbury in Christchurch, New Zealand, where I think the title on the degree, the field on the degree is engineering geology. But really what I was doing was taking engineering geology methods and applying these engineering geology methods in the realm of physical volcanology to understand how hydrothermal alteration changed the permeability and the strength of volcanic edifices. And I should be very clear that the work I'm presenting today has no affiliation with the US Geological Survey. They're quite strict about the work that is produced with their title or their affiliation goes through an internal review process. And this work has not done that. This work is strictly with the University of Canterbury. So I present to you as an affiliation with the University of Canterbury. And I would be remiss if they didn't get credit for what I'm going to share with you. Just for completeness sake, I'll add that I did my master's research at the University of Oregon in geochemistry and petrology on volcanic systems. I looked at the volatile contents of melt inclusions to understand the magma transport beneath andesitic and basaltic andesitic volcanoes in the Oregon Cascades. And before that, I spent a couple of years mapping metamorphic units on the East Coast of the United States in the Appalachians. So I'm just trying to say that I have a pretty diverse background. It's not that I have only worked in engineering geology or I've only worked in machine learning. Thank you for taking the time to listen to my work for my PhD research. And thanks for the invitation. It was a surprise, and I'm always happy to share my work. So I labeled today's talk, The Effects of Hydrothermal Alteration on Deformation in Volcanoes. And really, my PhD research has one unifying message, which, I'm jumping the gun. Let me start by saying that this work was not done in isolation. I worked with a fine range of collaborators. At the University of Canterbury, I worked with Ben Kennedy, Marlene Villeneuve, and Darren Gravely. I also worked with researchers at the University of Strasbourg in France, Mike Heap, Jamie Farquharson, and Terry Ruchley. I also have other collaborative connections with the University of Otago with Rosie Cole, GNS Science in New Zealand, Graham Leonard, and at the Technical University of Munich, Hans Gilg. So this is all to say that this work is it's rather international. It wasn't just done in New Zealand, and it wasn't just done by one group of researchers, but we really spanned many different disciplines. The unifying message from my combined PhD research really addressed how does hydrothermal alteration from shallow magma affect the petrophysical and geomechanical properties of a volcanic edifice. And from that, I took away three key findings. One is that in a volcanic edifice, alteration can introduce new weak rock masses, which contribute to edifice pressurization. Alteration can also inhibit shallow seismicity and may reduce the outgassing potential during deformation. Now that's a loaded 3 points, and that's what we're going to spend the rest of this presentation going into greater detail on. But let me start with where New Zealand is. And forgive me if this is a bit too introductory, but New Zealand is located in the South Pacific to the east of Australia. And New Zealand consists of two predominant tectonic environments. New Zealand hosts a subduction zone and a translational tectonic environment. Specifically, for the translational tectonic environment, the South Island has the Australian plate sliding against the Pacific plate. And that's what produces the Alpine Fault and the mountains for which the country is rather famous for. Then we have the subduction zone. The subduction zone is the product of the Pacific plate to the east, subducting beneath the Australian plate to the west. And that creates a volcanic arc. And it's this subduction zone and that volcanic arc that we're going to focus on. And I should add that when you hear about all the earthquakes in New Zealand, New Zealand's quite a mess in terms of hazards, simply because of this unique tectonic blend where you have subduction and translation. And somewhere between these two different regimes of tectonics, you have the plates trying to sort themselves out. As I often say to people unofficially, the countries are ripping itself apart. I don't know of any other place in the world where you have this transition between two tectonic environments. At any rate, I digress. Let's focus on that subduction zone up here in the North Island. Specifically, the subducting Pacific plate produces a volcanic arc that in New Zealand is labeled the TVZ, or the Taupo volcanic zone. The Taupo volcanic zone hosts the vast majority of the active geothermal and volcanic systems in the country. I should also add that the Taupo volcanic zone is a rifting graben. So the Taupo volcanic zone is dropping down as it fills with volcanic material. And this TVZ, this Taupo volcanic zone, is filled with several volcanoes and geothermal systems. For example, this photo on the left is taken from the eastern flank of Ruapehu volcano. This photo is taken from the northern flank of Ruapehu volcano, or facing north-northeast, and we see other volcanoes like Ngauruhoe volcano, also known, if you can forgive me, as Mount Doom in Lord of the Rings, but the indigenous name, the proper name is Ngauruhoe. Behind Ngauruhoe, we have Tongariro, for which all of this land is given the namesake of Tongariro National Park. This is to say that there's more than just Ruapehu in the Taupo volcanic zone. And of course, we have beyond the land, inside the Bay of Plenty, the volcanic arc continues. This photo here is from the eruption of White Island in 2019 that sadly and infamously killed many tourists. And the volcanic arc continues up the Kermadec Trench beyond frame here for at least 1,000 kilometers with the subduction of the Pacific plate beneath the Australian plate. Now, not all the volcanism in New Zealand is found inside the TVZ. This photo, again taken from Ruapehu, is toward the west. The star in the distance is Mount Taranaki, or simply Taranaki. Taranaki on this map is indicated again by this star and is located far in the back arc outside of the Taupo volcanic zone. My research for my PhD focused on Ruapehu. Ruapehu is found in the southernmost extent. It's the southernmost expression of volcanism in the TVZ. Specifically, Ruapehu is an andesitic stratovolcano. Let's start with this photo in the upper right. This is probably one of the better photos of Ruapehu that I have access to that gives you an idea about the general geomorphology and lithological disposition of Ruapehu. Ruapehu is often described as monotonously andesitic. I kid you not, they say monotonously andesitic in the literature. But the compositions can range in some cases to dacite, but admittedly, most of the lava flows of Ruapehu are andesitic. And I should add that most of these structural components of Ruapehu are lava flows 1 to 2, maybe 3 meters thick, interbedded with thin layers of ash and lahar deposit. For the sake of reference, this is Ruapehu in the background here, with Ngauruhoe in the midground, and then a new edifice for this presentation called Red Crater. This is taken from a famous walk in New Zealand called the Alpine Crossing. Back to Ruapehu though. Ruapehu erupts roughly every 20 years, and I emphasize roughly, but the eruptions tend to be rather minor, VEI 3 or 4. In other words, eruptions happen, air traffic gets shut down, but it's not going to devastate the landscape and obliterate the country. These eruptions are explosive, but they're not catastrophically explosive unless you're on the volcano when they happen. Ruapehu volcano has been mapped into 4 lithological units. And I have these units here from Whakapapa as the youngest down to Teharenga as the oldest. And Teharenga is really the formation that we're going to focus on today. Teharenga is roughly 250,000 years of age, and consequently has been subject to many periods of glaciation. And that glaciation has, in some cases, dissected the original stratigraphy of the lavas that were emplaced by Ruapehu. What that means is that in some cases, I should back up. So what has happened in one case is that glaciation exposed a fossil hydrothermal system. And that's what this photo is of down here. That fossil hydrothermal system is called Pinnacle Ridge by the locals. And at Pinnacle Ridge, you can walk up and put your hand on the crystalline magma chamber that drove hydrothermal fluids or hydrothermal convection inside the system. So this dark triangle is that magma chamber, now crystalline. And then you can walk out the alteration halo for several hundred meters. And at the edge of the alteration halo, you transition from hydrothermally altered andesite to unaltered andesite. What this means from the perspective of a geoscientist, you can walk up and you have this full complex in which you can investigate. So for my PhD, I approached this ridge and tried to sample from as many locations as possible to sample from different lithologies and different distances from the intrusion to try to investigate how that alteration affected the geomechanical properties of the host rock. With that said, the spacing that I collected from was not regular because although not apparent in this photo here, if I can refer you to this photo in the upper right, the topography of Pinnacle Ridge is quite precarious. You can't get everywhere. It's an oversteep and teleslope. And unfortunately, fatalities happen on this ridge every year. So we took caution, and when we couldn't get to some areas due to slope or rockfall, we didn't. Now, when I say geomechanically characterized, what do I mean? Well, I investigated the porosity and the permeability, that is the void space and the fluid flow through that void space in the different samples I collected. Specifically, I investigated the porosity and the permeability of intact sample size or intact samples. Similarly, with those intact samples, I measured the elastic wave velocity, that is the P wave and S wave velocity. Also, I investigated the strength. I did several hundreds, maybe even thousands of strength experiments. This included both uniaxial compressive strength, as well as triaxial deformation using a hook sill. Lastly, because these different attributes that I've mentioned thus far are focused on intact rock, I also looked at the discontinuities. I quantified the discontinuities in the rock masses from which I collected. And by discontinuities, I mean breaks in the rock, like faults and fractures and joints. Using the geological strength index by Hook and Brown, I'm able to assess the frequency, the interactions, the surface conditions of these discontinuities, and apply a number that I can then use for comparison and modeling. From collecting these different samples, I'm running out of time. Shoot, how much? I will speed up a bit, sorry. Okay. So from these different samples that I collected, or from all these different characterizations and samples, I broke the ridge down into 7 geotechnical units, 3 altered and 3 unaltered, specifically altered and unaltered intrusions, altered and unaltered dense coherent lava, altered and unaltered brecciated lava margins. And then I identified a 7th geotechnical unit, hydrothermal vein material. It wasn't great in extent on the volcano, but it was important because it was distinctly different geomechanically than the other geotechnical units. If we compare permeability versus porosity or log of permeability versus uniaxial compressive strength, we see that in general, the data tend to follow a trend across the 7 different geotechnical units. However, the hydrothermal vein material far off that trend line. If we look over here at compressive strength versus log of permeability, we again see that hydrothermal vein material falling off. And that's because the hydrothermal vein material is made of a different mineral composition than the other 6 geotechnical units. The hydrothermal vein material is made of hydrothermal precipitates. So this raises the question of, well, how does that hydrothermal vein material affect the stability of the volcano? From triaxial deformation experiments, I completed the Hook-Brown failure criteria for both intact and rock mass properties of the 7 geotechnical units, and then took all these different parameter data and put these data into finite element modeling or numerical modeling to investigate different scenarios with different degrees of fluid infiltration and hydrothermal vein conditions, such as no hydrothermal vein, vertical vein, and dipping vein, to see how pore pressure changed. And what I found in the current day configuration of Pinnacle Ridge, the hydrothermal vein in vertical and dipping configurations increased the pore pressure of the ridge. Now, with that said, the hydrothermal vein never decreased the strength factor of the current day configuration Pinnacle Ridge beneath 1, and that makes sense. Pinnacle Ridge is standing today. So we tried a different scenario. It's hypothesized that Pinnacle Ridge formed at below 500 meters depth before it was glacially dissected. So we ran the same conditions, but at 500 meters depth. And what we found is that, yes, again, the hydrothermal vein leads toward pressurization, but that pressurization then drops this factor of safety, or the strength factor, below 1. That is that under these conditions, the ridge has failed irreversibly. So what we find is that a hydrothermal vein can significantly reduce the factor of safety. It not only acts as a fluid barrier due to its lower permeability, but it's weak, and its stiffness is also lower. It localizes deformation and enhances pressure-induced instability. And if I have time, I'm going to briefly run through one last bit, an opportunity that we found while pursuing this study, which was, could we prove that hydrothermal alteration changed the failure mode of the volcanic rock? And what we found, I'm just collecting samples from the ridge. I take a sample back to the lab, I cut it open. And when I cut it open, I find that the rock hosts 2 forms of hydrothermal alteration: advanced argillic and intermediate argillic. They have different mineralogies and different porosities despite having the same protolith. Well, this presented us with an opportunity. Here we have a ceteris paribus condition where the only difference between these samples is the degree of alteration, the type of alteration. So after reviewing the literature, we wanted to identify an effective confining pressure under which one sample would perform ductily and the other sample would deform brittly. And if everything else the same, it would mean that the hydrothermal alteration causes change in deformation behavior. And that's what we found at 10 MPa effective confining pressure. Now, this has massive ramifications. Specifically, this means that, 10 MPa confining pressure is roughly 300 meters depth inside a volcanic edifice. That is much shallower than the previously modeled brittle ductile transition zone at several kilometers depth, or maybe 2 kilometers depth. It's an order of magnitude shallower. Also, the failure mode in ductile rock is often cataclastic pore collapse, and that does not induce a distinct seismic signal like that of brittle fracturing in brittle rocks. If you're relying on a seismic network to monitor a volcano, that cataclastic pore collapse might not be observed despite the increase in pressure in the volcano. You might not get that pre-eruptive signal. Also, ductile deformation often leads to lower permeability and compromises outgassing potential capabilities. The ductile rock high in the volcanic edifice could be contributing to overpressurization of a volcano. And although everything I've described is found in a fossil hydrothermal system on the flank of Ruapehu, the same material is found on top of Ruapehu in an active hydrothermal system. Moreover, these hydrothermally altered rocks from different geophysical surveys, like this aeromagnetic survey from Kurtzy 2020, find that the hydrothermal material extends deep into the volcano. Lastly, this hydrothermally altered rock is not limited to Ruapehu. It's found worldwide, like at White Island. It is heavily hypothesized that the explosion at White Island back in 2019 was partly due to the nature of the hydrothermally altered rock found on the volcano, or in the volcano, I should say. So in conclusion, hydrothermal alteration creates new weak rock masses, which can contribute to edifice pressurization. These new weak rock masses, or the hydrothermal alteration, can inhibit shallow seismicity and may reduce the outgassing potential during deformation. Thank you.